Hello there. Hello, friends. And welcome to your lucky day. As predicted, I should say, not advertised. Sometimes, by pure accident, my desktop gets revealed, and there's always something nice to look at on my desktop. Well, not a thing, but a person. And this particular person's picture, I again modified. All of my pictures have been modified in some way to either make them look nicer, or just general repairs, or to make something interesting, change the background, things like that. This one, the everything was great, but the face was. It's not the girl, but somehow the image was all cracked and full of jagged lines around the face, and it looked terrible. It was a real shame to see that. Nice picture like that would somehow got ruined. So I tried as best I could to, well, pretty much by hand. In this case, the reconstructor nose and this, like all this I had to fill in, and so you see I didn't get this right exactly. And here, I think that this here, it was so overexposed that you couldn't even make out that there was a nose here. It's just white, and I don't know. And somebody just posted that picture. I don't know how they could see what a disaster it was. But anyway, it's not a disaster now. I think it looks quite nice, although it is a bit bright on the bright side. It's a little bit on the bright side. Speaking about on the bright side, I hope that if you first introductions, just in case you landed here by accident, the topic of this playlist, not the channel, is something called a group, mathematical construct called a group. And in the last episode of this series, I ended off with the statement of 3 theorems. And if you haven't watched that one, I would suggest you go back and look at those theorems. And the other video, there's only 2 others, and see if you can prove them. They're not hard to prove. And as you're going to see now, I'm going to go through the proof. It's a completely mechanical process. No thinking involved, really, except for, I don't know, just recognizing which steps to take. I should note, there's a typo in the last video. I had an I here. It should have been A. I times A equals A. That's the definition for a left identity. This would hold true for any member of the group. And here are 3 theorems. Goodbye. Oh, maybe that background's too bright. I wanted that. Maybe I can darken it. You can't put it on the other side. This one's scary. It's too scary. Try this. What's that? It's not too bad. Okay, so right, that's a typo. Minor typo. I'm sure if you were paying attention, you would have noticed it. So proof of theorems 1, 2, 3. 1 to 3, not, well, it's also 1, 2, 3. 1 dash 3. Theorem 1. A group contains only one identity, I. It is both a right identity and a left identity. And so, for example, the repaired thing in brackets, just same as last time. Okay, now you can sort of see what's going to happen by this thing I drew in, but whatever. So just starting from axiom 4, this really does go here. Let me change the colors. Axiom 4 says that for every element A in the group, there exists another element called X. It could even be the same element, such that A times X is equal to the right identity. Okay, I haven't labeled it with any R. I could actually. There is a R subscript. There's no L subscript though. I haven't found one. Alright then. Now I'm just going to blunt. This is just completely by definition. I've taken this statement, and on the left hand side, I'm multiplying both sides of the equality by something equal, which is I in this case. So doing the same thing to both sides, and they should remain equal. Alright, now on the right hand side, I get I times I, and since I is a right identity, it is a right identity for this object, and therefore the result on this side is I. Okay? On this side, using by 1. Oh yeah, okay, I'm using this same expression that I times A times X equals A times, well, this follows because yeah, okay, right, sorry, that's what these circles are for. This is I, right? And this is also I, so now I'm substituting for this I the other way of writing I, which is A times X, so I can put that here. You see? It's funny how hard it is sometimes to come up with these things, you know. It's staring you in the face and you don't see it. But anyway, A times X is I. And here we have this equals I. So I can put this over on this side. So now I have I times A times X equals A times X. Okay, now recall, of course, that we have the associative axiom, which will be important for the next step. Now, by axiom 4, there exists an element called Y, let's say, in the group, such that X here times Y is equal to I. Every element has a right inverse, right? So in particular, x has a right inverse, and we're calling it y. All right. X, you'll recall, is A's inverse. Okay, so we have that, and so what we can do here is what am I doing? I'm multiplying y on the right hand side of this expression. So we're taking 3, this is 3 times y. Well, star. That equation is 3. Okay, so for clarity, put it the same color. Right? So we take equation 3 multiplied by y on the right, and that gives us this. Well, you'll notice the way that I've written the brackets. If we didn't have the associative axiom, this is the correct way to write this down. You'll notice that there are no triplets. Right? Everything is one thing times another thing in this expression. It's a binary operation. It only acts on 2 things, and the way these brackets have been organized is the way in which the product would have to be carried out, were we to multiply both sides on the right by y. Right? Y times all of this stuff. So there I put brackets around it, and y times all of this stuff, brackets. However, by axiom 2, star is associative, so we can fiddle with these brackets any way we like. So I put I times A here. I'm not changing the order. Remember, we don't know if this group is commutative. May or may not be. But I'm still allowed to move the brackets. I can change the order of multiplication, but not the direction. Alright, so now on this side, I've isolated the A out, and I've got x times y here. But x times y is the identity, the right identity. And here it is again, right identity. And here we have I times A. So we got A times I, which gives us A on the right hand side. And here we have I times A. I, recall, is the right identity. So we don't know anything yet about this, what this might be. But we know that this times the right identity should yield itself. That is, we need to have 2 steps here to do it in one. But I just did the right hand side first, and then this side second. Huh? Oh. I didn't need to actually, it's better to do it the other way. It's more instructive. It should go directly to this. No knowing. Because this here, I can just draw a line. How can I draw a line? Oh yeah, chain key binding. Thin line. Here I have something bounded. A thing times the right identity. See? So that the result of that product is the thing on the left. So I don't need that other step. this follows in one step. And so what that yields is I times A equals A. But I was the right identity, and now he's shown that it's also a left identity. So we've discovered the first part of the theorem, or the second part, sorry, is true. It's both a right and a left identity. Now, but we haven't shown yet if it's unique. That's coming up. Uniqueness of I. So now, suppose there exists another element in the group, gamma, having the same properties as I. That is, it's a right identity. Okay, we'll call it I1. So by definition, because this is a right identity, I times I1 gives I, right? That's axiom 3, using I1 as a right identity. But now we've just shown on the other page that I, our other I, is a left identity, right? Which means that we go back and show you it again. Our other I times anything gives the anything, right? Other I times anything gives anything. So we can use that result and come up with this expression. I times I1 is I1. But we've just shown that by definition, I times I1 is equal to I. So these two sides are equal, and therefore these two are equal, and therefore these two identities are the same element of the set. Okay? Now I've put a note here. What is being assumed here, another one of these things that you might not realize you're assuming, is another axiom that goes probably with every mathematical system, at least it involves algebra, which is the transitive property of equals. That is, it's spelled out explicitly in Euclid. If one quantity is equal to something and another quantity is equal to that same thing, then the two quantities have to be the same. Euclid spelled it out. If A equals C and B equals C, little c, then A equals B. That's this it's called the transitive property. Transitive meaning like transference. I think that's the right word anyway. We can transfer this A over to here, let's say, because well, it's an axiom. There's no because. This is taken to be self-evidently true. Okay, so my note here is I believe we're to take as self-evident truths any any axioms concerning statements with qualities, such as the one I just mentioned, and other things like if multiplying something on two sides of an expression doesn't change the equality. Again, those were made explicit in Euclid, not here. We're just taking them as given. But we don't have to take them as given. We could include them along with the four axioms that we already have. Those axioms are, I think, universal. There are no systems that violate those axioms that I know of. Okay. So we've established that it's unique, and that it's a left and it's a right identity. Now, sorry, there's one more thing to show, and we can start with a left identity, follow through the same logic, and show that a left identity must be unique and must also be a right identity. And so therefore it follows that there is only one identity, and it's unique, and it's both a left and a right identity, and so we're done. And the conclusion, this means as was to be shown, this little red thing. The other note here is so now from now on, I'll be using a symbol. I'm following a book here for this part anyway, and in that book, from this point onwards, they're using the symbol 1 for identity, and drop the star. Actually, they never used the star, but I've added them back in. But now I'm going to drop the star and use the brackets only when there might be some ambiguity. If the operation is associative, you don't need brackets because it can be carried out in any order you like. Next, part theorem 2. If A and X are elements of the group, and A times X is I, so X is a right inverse of A, then this says that X is also a left inverse of A. Further, there is no other element in the group X that satisfies either of these qualities, and that makes X unique. Okay. This is easy to show. Given the definition of a group, okay, the notation is a lot cleaner. You probably noticed. What we have here is we're starting with AX equals 1 and XY equals 1. Okay, so I'm going to note that by the definition of group, A must have a right identity. So there is an X satisfying this. Similarly, X has a right identity, so there is a Y satisfying this. Y, of course, is the inverse of A's right inverse. Well, it's the right inverse of A's right inverse. Okay? So we start with A times X equals 1. And on the left-hand side, what have I got here? Where that Y? Oh, 1. AX equals 1. I'm multiplying by Y, I see. So we multiplying through by Y on the left. this 1 times y gives y. So the identity is good on the left or the right. Okay. Now this business is working out y times ax, or ax times y. If you read it from left to right. No, this is just saying the same thing. So I don't really need two of these. So y times the left hand side is left hand side times y is ax times y, and using the associative property we can switch the brackets around the xy, and that turns the xy into a 1. Okay. And that gives us a. So what we have here is well, it's just a. It's a big deal. Hang on a sec here. I'm missing a step, I think. If I multiply, let me just read what I've written. This says a, not y. Hang on, I removed something important. Okay. If I had multiplied through by y, what am I missing here? Ax, no, it said the same thing. That certainly gives a. Oh, but ax is equal to 1, see? So this is just y. I see, okay. It's hard. It's funny how... because you think nothing's happened, right? That everything canceled and I got a equals a, right? Well, I don't really need to... I don't really need to have this part at all. Oh no, I do need that. I need to. I want to show that y and a are the same, right? So if I multiply through by y, then this would say y, but that's not what I did. That's not what happened. What did happen? Let's do it slowly. Do it again. If I multiply both sides of this expression by y on the left, then I get times this one. Well, I'm using a star for this one. 1 times y, and here I have ax times y, right? Correct? Okay. So this side equals y, because the left identity equals right identity business. And this side I can rearrange like this. But xy is equal to 1, and I get a times 1 equals y, and therefore y equals a. Got it? Okay. Alright, now since xy equals 1 and y equals a, It's another tricky one. It's hard to see them. X, y equals 1 and y equals a. Okay. Do you see it? Do you see the answer? We're trying to show that that x here is a left identity. Keep that in mind. Okay, we've just discovered y and a are identical, so we can put an a in here instead of the y that's already there, and we get xa equals 1, so x is a left inverse of a. See? xa equals 1 and ax equals 1. Use my circle for that. Maybe not that color. Maybe not that size. Just bigger. Oh, it's radius, of course. Okay, we have that, and we have this. Too small. And these are one left, one right. Okay, so that part is shown. And every right inverse is also a left inverse. Doesn't mean that there aren't others around that we have to prove. Now we want to suppose that maybe there's another right inverse for A. So we start with this again. Multiply by x, which is the other inverse, the one that we had already, on the left of this. That gives xa x1, and that's equal to x. Why is that equal to x? Because of this and this. Right? This ax1 is the same as this, so this is a 1. So we get x times 1, and that gives x. On this side, where we had a 1, all I did was multiply by x. Okay, fair enough. Oh, and now we're going to use the fact that we proved already that x is a left inverse of a. No. What we're doing is we're taking this expression, and instead of doing these two together, we do these two together, alright? And that we know gives us 1 because x is a left, the other x is a left inverse. Because xa equals 1, right? So xa equals 1, and then we get our identity, which is also a left identity, group. And so this also evaluates to x1. So what we have here is x equals x1, and so therefore any other right identities have to be equal to the right identity that we have, and it's also our right identity is also a left identity. Still though, that doesn't completely show that there might possibly be two left identities. So what we do is start with the same assumption on the left, we'll run through the same argument on the left, and we'll find the supposed other left identity is the one we already had, and that completes the proof. Okay. Now all of this is really quite simple, really. It's tricky to see, and that's what makes group theory difficult. Is not that the concepts are always very difficult. Sometimes they are, but sometimes the thing that you're looking at is so simple that you can't see it, if you know what I mean. All right. Now, since the inverses are unique and work on both sides and everything, it's fair for us to assign a special symbol, namely this one, for inverse element, and just analogously with numbers, we get this. We have this result. This is called the inverse of A, and since these inverses they commute, they're commutative. The inverses are commutative with each other. You can write this down just as you do in regular algebra. Now it should be pretty obvious that A is the inverse of A inverse, right? Because here is A inverse multiplied by something and getting 1. That something that it's multiplied by is A. So A is the inverse of A inverse. In other words, A inverse inverse equals A. All right? That's kind of an interesting thing, actually, if you hadn't noticed before, that if we were constructing a group where the operator was more like something like plus, then we would represent an inverse as and like a negative, right? And this is sort of telling us that minus 1 times minus 1 is 1. Not exactly, but actually that does follow it eventually. When one gets to the other topic that is similar to groups, which is when you add another operator to your system, and then you get something called field, and fields have that property. Scholium. Yeah, well, I'm not going to note my own comment, but if you recall, a scholium is a minor or trivial consequence of something just discovered that is not that doesn't have sufficient importance to be granted the title corollary. It's just a minor nothing consequence. And this particular scholium, as I've called it, they didn't give me a book. The author wouldn't know this word anyway, I'm sure. Being German. Well, maybe. It's a Greek word. So. We simply form this product, B inverse times A inverse, and multiply that by AB. Then, because of the way this is set up in reverse order, the A's are going to cancel to make an I, and then the B's are going to cancel to make an I, just as I've indicated, and in the end you end up with an I. So the inverse of AB happens to be this, B inverse times A inverse. Just a little, nothing thing fell out of the last theorem. Finally, theorem 3. If A and B are two elements of a group, and one and only one, then one and only one element of the group satisfies the equation AY equals B. I should write it in the modern way. Modern, meaning within the last few minutes. Okay. Only one solution to that equation. Okay, now let's see why that might be. Well, first we note that this happens to be a solution. If you plug it in directly, A inverse times B here, then you're going to get A right? If I plug that expression in for y, then that gives me this, which then using the associative thing that allows me to knock these two off and turn them into an I, and then I get B equals B. So that's already one solution that's known. Okay, so we can verify that by direct substitution. Okay, now let's suppose that first I'm labeling this element X, just so for clarity. This here will be called X. A known solution, and now let's see if maybe there's another solution. So let's suppose there's another solution, X2. Multiplying the left-hand side of this expression, if it is a solution, multiplying by minus 1, A inverse, that A inverse cancels with the A, and we get X2, and on this side we get A inverse B, and so the two are the same. So therefore there's only one solution to equality. The equation here should be underlined, maybe. There's only one solution to this equation, namely this value, whatever it is. And that completes the proof of those three theorems. And so therefore, our group is looking more and more like, something like numbers. Many of the properties of systems of numbers that you're familiar with are similar to this, right? Now, is that all I have? I think that's it. I thought I had something I wanted to add extra. I guess not. Well, let me just check something. The girl. Hang on. Okay, I'm going to make my life easy on myself and save myself some typing. Usually I try to reword these things to make it easier for me to read. But there's just a little summary here of what we know so far. Okay, so we know that certain these properties. Alright. Now, I don't know what this is for. What was 3? 3 is the theorem. Okay, well anyway, I just want to, this is a little summary here. A group is a set that has the following properties. The elements of the set may be multiplied according to some definite law, and the result, the product of the multiplication of any two elements, is a definite element in the set. At one point I said the output could be 1 or 2, and that was bad wording. What I meant to say is that the L operator I introduced might be commutative or not, right? It might produce, for a given pair, 2 possible numbers or 1. One product. A product has a definite value, and there's only one value for a given product. But there might be 2 values for a given pair, is what I was trying to say. Okay, the multiplication is associative. I can't stress with enough emphasis how important the associative principle is. If you don't have associative principle available, then there's really no use in using algebra, right, in your system. Use something else, because algebra is only of use when you can do things like, add something to both sides and break the elements up and so on. Without the associative property, you're stuck at every turn. You can't deduce anything from any equations because you can't recombine things in a different way to form a different output. Okay, so in a group there's this special element called I, and it's called the identity element. It's analogous to 1 if in multiplication, say, everything times 1 is equal to itself. It's also analogous to 0 for kinds of operations that resemble addition. A kind of operation that resembles addition is powers, like logarithms. Multiply if you have something like a to the x times a to the b or something equals a to b. I can do bracket actually. Whoops, it's got to go up too. I have plus for this too. I think I have b. Most of the superscripts have almost all of them. It's easier to see once it's right. So multiplication of powers of a number is identical to addition, right? A group based on powers of a certain element. In fact, that's one way that subgroups, like part of a group that's a group on its own of another group, are formed. by taking one element and multiplying it by itself over and over and over again. Now those subgroups are, the way they behave is analogous to addition, because as you can see here, the product is really just a sum. And the identity element is just like 0, right? But it's not 0, it's a to the 0, which is in fact 1, which is the multiplicative identity. So there's a one-to-one correspondence in those cases from multiplication to addition. An interesting fact, and you'll see it come up later. Okay, we got a unique, everything has a unique inverse, and it works on both sides. Groups can be finite or not finite. Groups that are finite, if a group is finite, then the number of its elements has a special name assigned to it. It's called the order of the group. Okay. If it's an infinite group, it doesn't have an order. They're just called infinite. And they give one example, I think. And now the next example is in this book anyway, the permutation groups. And these are the elements of this group are not numbers, okay? And that's probably what they're trying to demonstrate here. An element of a group is not restricted to numbers. What the elements of this group are rearrangements of things. You know, like say you had 5 playing cards, you know, you're kind of, or 52 playing cards or something, and you're interested in studying poker hands. Then you would use groups. You could use group theory and think of the various rearrangements of the deck as elements of a group. And you can think of, and the operator times for these permutations is the process of performing one permutation first, and then performing the second permutation on the result of the first permutation, like a function of a function, you know, a composition, f of g of x. Well, it turns out that that operator for permutations, together with a certain set of elements, forms a group. And they're called permutation groups, and they're extremely important in not just you know, for playing around, but in physics and statistical theory, in probability theory, and you know, this notation might be familiar to you, although this is not the M choose N thing. It's something else. So I might look at those permutation groups. Another type of group consists of, let's say, a certain class of continuous functions and the function composition operator. Okay, those can form groups. The types of things that actually form groups generally don't have anything to do with numbers, and the elements of the group are of no interest to a group. Somebody who studies group theory couldn't care less about the elements. All that's important is how the operator behaves. the elements are irrelevant. Could be anything. An example of a group given somewhere, either this book or the other one I have was the set of displacements. Okay, in 2 or 3-dimensional space, that forms a group. The operator is the vector sum of displacements. The identity element is the null displacement. Don't move. Every element in the set of displacements has an inverse, which is essentially the displacement which would bring you back to where you started. You see, it doesn't even matter what the things are. That group behaves just like vectors, regular old vectors. Okay, well, anyway, we'll get to that at a later date. See you.